Welcome to this lecture. In this lecture, I am going to talk about matrix formulation of quantum mechanics as described by Heisenberg. That how Heisenberg start doing quantum mechanics using matrices, how he got the idea. So for that, let us start with the classical mechanics. So let us recapitulate classical mechanics, few results of classical mechanics. Let us recapitulate it. So in classical mechanics, we have learned about Poisson bracket. So let us describe it. So consider F is a function of Q and P, where Q is a generalized position and P is a generalized momentum. And I am considering two functions F and G, which are depending upon Q and P. So that means these are the two functions in phase space. Here Q is known as generalized position and P is known as generalized momentum. Now Poisson bracket is defined as it is represented in curly bracket. So curly F over curly Qi comma curly G over curly Pi minus curly F over curly Pi and curly F over curly it is curly G over curly Qi. Let me call it as equation number 1. Also, we know that this F is a function of this Q, P and T. So therefore, its differential can be written as df upon dt. It must be equal to curly F over curly Pi by curly T plus curly F over, or what I can do, I can start writing it first of all with the Qi curly Qi over curly T plus curly curly F over curly Pi and curly Pi over curly T plus curly F over curly T. So let me call it as equation number 2. Sorry, I will no need to write down it as equation. Also, I know from this what we call, let us recall canonical equations of Hamilton. Canonical equations of Hamilton that is curly Pi over curly T is equal to minus curly H over curly Qi and curly Qi over curly T is equal to curly H over curly Pi. That means curly Qi over curly T, this can be written as curly H over curly Pi And here curly pi over curly this can be replaced as curly h over curly qi with negative sign. So if I use these results here, then what I am getting, that is curly f over curly qi into curly h over curly pi minus curly f over curly pi into curly h over curly qi, and this negative sign will be here, so it makes it negative, plus curly f over curly t, and this is like a Poisson bracket of f and h. So that means df over dt can be written as Poisson bracket of f and h plus curly f over curly t, right? Similarly, we can evaluate this qi, Poisson bracket of qi pj, it can be written as curly qi over curly qi into curly pj over curly pi minus curly qi over curly pi and curly pj over curly qi. So it is pj and it is qi and it is qi and pj, so their derivative will be equal to 0 and its derivative will be equal to 1. And let us have a look at. So it is pj with respect to pi, so that means its value will be 1 or 0, means if I is equal to j, then their derivative will be 1 and otherwise it will be 0, right? So it's like a delta function. So that means this qi pj, their commutator is equal to delta ij, right? And similarly, let me call it as say it is equation number, okay, let me go back. Yeah, let me call it as equation number 2, and this is equation number 3. And similarly, we can prove that qi qj, their Poisson bracket will be equal to 0. We can prove, but there I am just recapitulating these results, right? So this is a result from classical mechanics. Now let us recall Bohr's postulate and Bohr-Sommerfeld quantization. So as we know from history of quantum mechanics that Bohr's postulates and Bohr-Sommerfeld quantization condition these two, Bohr postulate and Bohr-Sommerfeld quantization condition, they both collectively constitute the old quantum theory. Basically, Bohr's postulate is a special case of Bohr-Sommerfeld quantization. So, and what is Bohr's postulate? Bohr's postulate is that MBR is equal to NH cross. This is Bohr's quantization condition for the angular momentum. But this could not be explained, could not be applied for complicated cases. So this equation modifies to new equation given by Sommerfeld. He used the idea of action integral and action integral we have studied in the classical mechanics. Right. So first of all, let us talk about like action integral. Then we will see that how Sommerfeld used the idea of action integral to derive the quantization condition. So action integral is defined as this S is equal to L dt. It's a Lagrangian from T1 to T2. Then this is known as action integral. Here L is the Lagrangian, and this Lagrangian is a function of Qt, Q dot T or T, or sometimes we may write it as Qt, Pt and T. So this is the action integral, and here it's a Lagrangian and it is a function of Q, P and T. And we can also express this equation as what we call we can also define another integral S naught as P dq, and this is defined as this S naught is defined as an integral of generalized momentum along a path in generalized coordinate. And also, according to Aperture's principle, true path is a path for which S naught is stationary, right? So this is stationary path is the idea from the classical mechanics from the action integral. So that means if we use equation 5 and 7, Sommerfeld suggested that what he suggested? He suggested that integral P dq must be equal to NH, or we may write it as in a different manner. It is P dq by dt into dt, and its integral from 0 to t, it is NH. And let me call it as equation number 8. And using equation number 8, one can derive the relation that MBR is equal to NH cross. And in a generalized form, equation 8 can be written as that is PR dqr is for rth radius, or where the radius is r, then this integral is basically nrh, and where r can take 1, 2 and 3 and so on, right? So this is known as this is not the radius, but r is representing some integral values. So this equation number 9 is basically Bohr-Sommerfeld quantization rule. Now, two things are there. One is the Bohr's postulate, and another is Bohr-Sommerfeld quantization rule. They both helped Heisenberg to develop matrix formulation for the quantum mechanics. So for this, let us proceed in the following manner, at what Heisenberg did. So let us start with the motion of a particle. So particle is moving in a fixed orbit. Particle means electron. Moving in a fixed orbit. In this way, electron is moving in a fixed orbit with periodic behavior. And its motion is represented by xt, and it is a periodic. That's why we are representing this xt in Fourier representation. as xt is a period in nature. So that's why I'm representing it in the, or this Heisenberg represented it in the Fourier form. So that means in the Fourier form, xt can be written as summation n varies from minus infinity to plus infinity. It is xn exponential of 2 pi iota nt by capital T, as omega n is equal to 2 pi n by T, means frequency in the nth orbit, and 1 by T is the linear frequency nu. So therefore exponential iota omega nt can be written as exponential iota 2 pi n capital T into T, right? So we have expressed it in this form here. We have used this simple idea. Also, this xn is a complex quantity. So if it is a complex quantity, that means xn must be equal to x minus n star. Now let us assume that initially particle in nth orbit then emitted a photon. When moves to mth orbit. Here n is greater than m. So the energy of photon is En minus Em, and frequency of the photon will be nu is equal to En minus Em divided by h, or I can call it as omega is equal to E minus Cm over h cross. Now define a quantity xnm having frequency En minus Em divided by h, and its time evolution is defined as time evolution Enmt is equal to Enm0 exponential of 2 pi iota En minus Em divided by h into t. So this equation is basically, this is known as original form of Heisenberg's equation of motion. Now, what I will do, now consider two physical quantities. Now, consider two physical quantities one is the x and m and another is the p and m. One corresponds to position and another corresponds to momentum. And the product of these two quantities is simply the convolution of Fourier coefficients you can read convolution of Fourier coefficients in any book on Fourier transform or the Fourier series, and these two quantities basically evolved with time, and their product pair can be found simply by using the convolution of Fourier coefficients. So that means xp mn can be written as it is k is equal to 0 to infinity xmk and pkn. In some books, this convolution can be written either in the form of integral or in the form of summation. So here I am using the idea of summation. And if I recall Cij, it can be written as aik and bkj and summation over k. So this is the definition of matrix product. This is the definition of matrix product. So that means this part here which we are getting, it looks like a matrix product. But Heisenberg is not aware about this result, that it is from the it looks like a matrix product. So later on, Bohr pointed out it. Bohr pointed out that equation number 12, it looks like matrix product, and this thing is pointed out by Bohr, and later Bohr collaborated with Pascal Jordan and a matrix mechanics was developed. That means new formulation starts growing, known as the matrix formulation for the quantum mechanics. Thus, matrix mechanics was introduced by Werner Heisenberg, Max Born, and Pascal Jordan, in 1925, what was not immediately accepted. Even Born also discussed the idea with the Pauli, but he didn't recognize his idea. Means Born discussed the idea of this matrix product represented by Heisenberg to Pauli, but Pauli didn't recognize that. Then he discussed it with Jordan, and then Jordan and the Born and Heisenberg tried to develop the matrix mechanics. Even around 1925, Track also doing matrix formulation for quantum mechanics, but his notations are a little bit different. When he saw the paper of Heisenberg, then he realized that he was doing the things in the same manner as he is doing, but then he developed in the matrix mechanics in the different notations, and give results for the relativistic quantum mechanics, right? So I will talk about that later on, and let us discuss another very important result of matrices, that if A and B are two matrices, then need not necessarily that AB is not equal to PA. That is, AB minus BA is not equal to 0. Also, Heisenberg derived that X and K, PKN minus P and K, and XKN, this summation over K is basically equal to iota H cross 2 pi delta NM, or simply XP minus PX. It can be written as, it's a commutator of position and momentum. It is known as commutator. I will talk about it later. And it is equal to iota H cross 2 pi delta NM. And this looks like a Poisson bracket. So if I recall Poisson bracket, then this Poisson bracket of X and P is equal to delta NM. So that means this XP is related to this Poisson bracket, means commutator of Poisson commutator will be related to the Poisson bracket in this manner, right? So this is a very important result connecting quantum mechanics and the classical mechanics, because this is the classical mechanics result and this is the quantum mechanical result, right? So this relationship is a very important relationship which connect Poisson bracket and the commutator. So that's all. So thanks for watching this video. In this lecture, I briefly talk about that why matrix mechanics is so important in quantum mechanics. So in the next lecture, I will talk about basics of a brief review of matrix algebra, which is useful in quantum mechanics. So thanks again.